like what we call the standard type of projectile motion, where the projection is done from a horizontal surface obliquely, and the object which is in projectile motion, it returns back to the same horizontal plane. So today we will also look at some variations of that, but first of all we will look at some applications of especially the equation of trajectory, which is something that we derive towards the end, apart from all the standard formulae and equations. So let's start with a quick recap of the essential concepts of projectile motion, the standard projectile motion, that is. Okay. So talking about the standard example of projectile motion. So let's say this is the horizontal plane from which the projection has happened at a projection velocity u, which is at projection angle theta with respect to the horizontal plane. So if this is when we start our stopwatch or start the time measurement, then the projectile goes off in a path like this and comes back to this position. And now we also, what we do in the standard situation, we take the origin of our coordinate frame at the point of projection. Okay. We take the x-axis as the horizontal axis. Yeah, we will discuss doubts from the worksheet also, don't worry. Okay. So going in this sort of direction, so at some general time t, if we want to find the velocity vector and we want to find the coordinates, and through that we want to find all these special properties, that is the maximum height, the horizontal range, okay, the final impact velocity, the time of flight, and the horizontal range and all that. So we had seen the way to do all this is by the component method of kinematics. Okay, so along the x component, what is happening is the initial velocity is u cos theta and the acceleration is 0. So the x component of velocity at any time t, this is just constant because there is no acceleration, and the x component of displacement becomes u cos theta t. Okay, and similarly along the y-axis, we had seen that the initial velocity is the component u sine theta, but the acceleration is minus g because we have taken the y-axis upwards. Okay, so from this we see that at any instant of time t, the y component of velocity becomes u sine theta minus gt, and the y component of displacement becomes u sine theta t minus half gt square. So these equations represent instantaneous x component of motion. These represent instantaneous y components of motion. So you can combine them and say that at any instant of time t, the x coordinate is u cos theta t, and the y coordinate is u sine theta t minus half gt square, whereas the instantaneous velocity is u cos theta I cap plus u sine theta minus gt. So in solving anything that is related to what is happening at a certain instant of time from the time of projection, we have to use these two equations: the position as a function of time, or the coordinates as a function of time, and the velocity as a function of time. Whereas using these equations, we had seen the standard formula that we have is that maximum height is u square sine square theta by 2g, or we can understand it as uy square by 2g. Okay. And we had seen that at t equal to t by 2, the y coordinate becomes the maximum height, the x coordinate is half the range. Okay. Whereas the range was given by the formula u square sine 2 theta by g, or we can also interpret the range as x component of velocity into time of flight. This was the other standard formula. And the third and final standard formula was time of flight is 2u sine theta by g, or that can be written as 2 times uy divided by g. So these were the standard sort of things. Okay. Now the last thing that we discussed in terms of formulae and equations was equation of trajectory. Okay, that
So,
is, yes.
so in the x component at t equal to t, it's v or u x.
It's Vx beta. The velocity at any instant of time along the x-axis. The
Okay.
instantaneous velocity we always write with the symbol v, whereas the initial velocity we write with the symbol u. But you will notice here that Vx is actually equal to ux. Why? Because Ax is 0. Understood? No?
So got it, got it.
Whereas in the case of the y component, you can see that's not the case. Vy is not equal to uy because there is acceleration. You know?
Yes, sir.
Okay. And one more thing to understand here is that at t equal to capital T, the total time of flight, the x coordinate becomes the range, the y coordinate becomes 0, and the velocity actually becomes u cos theta I cap minus u sin theta j cap, which is why we understand that the impact speed is equal to the speed of projection. Okay. Whereas also when it reaches the highest point at time t by 2, at that instant the velocity is what type? It is only horizontal. The vertical component of velocity is 0 at that moment. So when the particle is at this highest point here, not only is the x coordinate half the range, but the velocity is only u cos theta and those kind of things. Okay, so these are the standard things. Now, equation of trajectory was the last thing we had discussed, and today we will concentrate on some examples of usage of equation of trajectory also. So equation of trajectory basically came from these two equations, from x as a function of time and y as a function of time, eliminating t from these two equations. So eliminating the variable of t from equation 1 and 2, we get the relation between x and y. So we got that y is equal to x tan theta minus half gx square upon u square cos square theta. Now we're going to concentrate a little bit on the applications of this equation in today's session. Okay, so just make sure that all these concepts are clear. Okay? You don't need to write this in detail because you've seen this in the previous lecture, but just go over these equations once, the equations as well as the formulae. Okay, the equations are equation 1 and 2, and these two that I have tick marked over here, and these are the standard formulae, whereas this one here is the equation of trajectory. Okay, so this also becomes important, and I've explained how it comes from equation 1 and 2. Okay, the exact derivation was done in the last lecture, but at this stage it's more important to just understand the derivation. So just make sure this is clear. If there's any doubt in any of these equations or formulae, just let me know. I'll explain again. Okay.
So,
Yes.
sir, an equation of trajectory,
Hmm.
what do we really mean by eliminating t?
Eliminating t is basically, see kya ho raha hai na, x here is in terms of t. In the first equation, you see what is the variable, it's t, and what is the dependent variable, it's x. Okay.
Yes.
Similarly, in the second equation, sorry, the second equation is this one, not this one. It's y as a function of time. So second equation, what is the variable? The independent variable is time, and the dependent variable is y. Now, how we have got the equation of trajectory? We have got it by removing time between these two equations. See the equation of trajectory, it's a relation between x and y. There is no t. So how it has been derived? By eliminating t between these two equations. So remember what we had done? We had substituted the value of t from the first equation as what? X upon u cos theta. We had substituted that in the second equation, and then that is given us.
Got it.
So that's what we mean by eliminating t. Okay. So the equation comes by doing that algebra, that we eliminate the variable of time using the two equations. So we're getting a relationship between y and x, and
So,
that
sir,
relationship.
instead of saying the word eliminating, we can use substituting.
You can, it's one and the same thing. No? Elimination and substitution is in that sense the same thing. They're playing the same role over here. Okay. But essentially, see, what we have to do is you have to remove t from the equation. You have to find the relation between x and y instead of x and t and y and t. So hence we are using the term eliminating. That's a mathematical term. It's not so important here. The important thing is finally what we are getting. We are getting the relation between x and y. So what this equation represents? It represents a relationship that is satisfied by every point on this path. You see the path or the trajectory the projectile is going through. Na? So at
Yeah.
different time, different coordinates, different set of coordinates, but every one of those points satisfies this equation that is over here. So that is why this is called the equation of trajectory, because it represents the path or the trajectory, right?
Yeah, sir.
Okay. So now now we'll discuss a little bit more about this equation of trajectory. So the first important thing you can see here is that y is a quadratic function of, or it's a quadratic relation of x. It's the relation of the type y is equal to some constant into x minus some constant into x square, where a is how much? It is tan theta, which is a constant. No? Tan theta is not varying with time because theta was the angle of projection. And b is how much? It is half g upon u square cos square theta. So again, it's a constant, no? Because u was the initial velocity, theta is the angle of projection, g is the uniform acceleration due to gravity. So a and b are just constants over here. So what kind of relationship there is between y and x? It's a quadratic relation. So if it's a quadratic relation, what does it tell us? That the trajectory or the path is of what shape? It is parabolic. The trajectory or path has a parabola shape or a parabolic path. So that means when we draw that curve that represents the actual path along which that particle is going, it's mathematically what is that path called? In coordinate geometry, it is called a parabola. It is not a semicircle or it is not an ellipse or something like that. It is exactly what's the name given to that path. It's a parabola. So that's one thing. This is the parabolic trajectory of the projectile. Okay, now one more thing. So you can just note down these points over here, equation of trajectory onwards.
Sir, what is written there in after B? Like,
After B, half
yeah,
g upon
in
u square
brackets, in
cos.
brackets.
It's a constant. So this term capital B is a constant. It's not a variable.
Okay, sir. Yeah.
Just like capital A is also a constant. It's tan theta.
Yes, sir.
Okay, now one more very interesting thing here is that we can write the equation of trajectory in a slightly different manner. Okay. So we will write the equation of trajectory in terms of the horizontal range and the angle of projection. Instead of in terms of u and theta, we write it in terms of this. So we start with the equation that we've already derived, x tan theta minus half gx square upon u square cos square theta. But next what we'll do is we'll take x tan theta common. So if we take x tan theta common, in the bracket we have 1 minus half gx upon u square cos square theta into 1 by tan theta we'll have to do because we have taken tan theta common outside. Okay. So when you do this, now you can see here that this term u square cos square theta into tan theta is actually nothing but u square sin theta cos theta. So this whole term 2u square sin theta cos theta by g is nothing but the range. Okay. So now Okay, so you can see that this term half gx square upon u square cos square theta into 1 by tan theta. It can be written as x square upon, sorry, x is there, not x square. I've already taken x common outside earlier. Okay. So this whole term that is there, the second term, it can be written as x upon u square sine theta cos theta by g, which can further be written as x upon u square sine 2 theta by g, which can be written as x divided by r. So that means this whole second term that we have, this term, it can be directly written as just x by r. So that makes the equation of trajectory a very simple type of equation in terms of capital R. It is x tan theta into 1 minus x divided by r, where r is the horizontal range, where r is given by this formula u square sine 2 theta by g, but it is the horizontal range. So this is another way of expressing the equation of trajectory instead of such a complicated equation above this one, x tan theta minus half gx square upon u square cos square theta. It can be just simplified and written in terms of range, and it's very simple. It's x tan theta, the whole thing multiplied by 1 minus x by r. Now this is also a very useful way of expressing it. When we are actually applying it in problems, we will see that this is a very useful form of this. Okay, so this is a very useful form for equation of trajectory for applications in numerical problems. Okay, so that is the reason why we are writing it like this. Okay, both mean one and the same thing, the above equation and this one. But when we write it in the form below in terms of capital R, it's a very convenient way, form for the equation when we are solving problems. And that's what we'll discuss next with some examples. So just make a note of this small set of steps also.
Sir,
Yes.
this is like the polar coordinate system representation of this.
नहीं बेटा, polar coordinate system में क्या होता है ना, you express the coordinates of any time point in terms of small r and theta, where small r is the distance from the origin and theta is the angle that the position vector is making with the angle with the x-axis. So there r and theta are variables, but here r and theta are constants. You understanding better?
Yes.
This is a relation still between x and y, no? So we are using Cartesian system. See the equation, it's relating x and y coordinates. So wherever you have x and y coordinates, you're still in Cartesian system. You're not in polar system. You understanding the point?
Okay, sir. Yes.
In polar system, what you do is the coordinates of a point are not in terms of x, y. They are in terms of r and theta. Okay, so that's something else we will learn that at a later stage when we're doing circular motion. Okay.
Okay, sir. Like in this case, the Cartesian system will help us out, but like आगे जाके we have to switch to that.
Yes, we are actually still solving everything in terms of the Cartesian system, in terms of x, y coordinates. Okay, so let's see some examples of questions where this becomes very useful, this formula. So for example, if we have a very, very direct type of question that given that a projectile has a range of, let's say, 240 meters and a maximum height of h equal to, let's say, 45 meters. Okay, find the angle of projection. Now I'll express two different methods of solving this question. Okay, method one is the formula based method, which most people will apply. There's nothing wrong with this, but is so range's formula is u square sine 2 theta by g. So here it is given to us that u square sine 2 theta by g is equal to 240 meters. Okay. So this is my equation one, and the formula for maximum height is u square sine square theta by 2g. So here it's given that that value should be equal to 45 meters. That's my equation two. Now from this we want to find theta. Okay, so what we'll do is we'll take equation one and divide it by equation two. So that will give us u square will cancel out. So we'll get 2 times sine 2 theta divided by sine square theta. Okay, just check. So you should be
Yes.
getting this. And much now? 5 will go.
Can open sine to theta. Can
Sorry?
open sine to theta.
We will have to open sine to theta also. Okay, I'm just completing this. So if we divide by 5,
40.
9. Okay, so this is further something like this. 16 by 3 we are getting.
Yes, sir.
Okay, and on this side what we'll get 2 times, like you said, we open sine theta. So 2 sine theta cos theta divided by sine square theta. So we can do this. Okay, and we can. Okay. So we have cos theta by sine theta. Okay, which is basically cot theta is equal to 4 by 3. So we can invert that and we can say that okay, tan theta is equal to 3 by 4. So that means theta is how much? It is 37 degrees. So it's not too bad, just couple of steps, but there's all this thing you have to do. So note down this method. Now, next is we will use the shortcut method and see how this can be done in one step. And that is by using the equation of trajectory method. Okay, so hope this method was clear to all of you. Now, using the equation of trajectory, you have the relation y is equal to x tan theta into 1 minus x by r. Now, in this problem, it is given to us that r is 240 meters and maximum height is how much now? 45 meters. We want to find theta. Now, we also know that at x equal to r by 2, the value of y becomes how much? H, because of that symmetry. Because of the symmetry of the projectile motion that we discussed earlier. At the moment when it reaches the maximum height, this horizontal distance is r by 2. 2 comma h. So this has to satisfy the equation of trajectory. So substitute this in this. So what it tells us that y is equal to h when x is equal to r by 2. So this gives us a very nice relationship between the maximum height and the range. You can see it is r by 2 tan theta into 1 minus 1 by 2, which is 1 by 4. So there is apparently a special relationship between these two quantities, and this is just this. And as you can see, the data of this question is just direct for this now. So when I substitute this as 45 and this, okay, I get directly that tan theta is 45 divided by 60, that is 3 by 4. So that means theta is equal to 37 degrees. So it gives us a much more direct way of solving. So now how I understood, how I will be able to gauge by looking at a question that equation of trajectory will give me a shortcut method. Anything that does not involve time, okay, is a geometrical thing. Okay, so here notice that in the question, okay, both the data given, okay, and the unknown quantity asked, the one we have to calculate, okay, both these things are time independent. Okay. So this implies that using equation of trajectory will most likely be the shortest method. It is like a hint. Okay, it's not maybe for all each and every question, but most questions, what will happen is that if the question is of this type, that neither the data given nor the unknown quantity asked has anything to do with time, then equation of trajectory is probably going to give us an easy way of solving the question.
So,
Yes.
so can you re-explain why y is equal to h, which is the max height?
No, it is that when x is equal to r by 2, y is equal to h, because that is the midpoint of the projectile motion. No? See the diagram on the left, you will understand what I'm saying.
Yeah, sir.
Understood the point? No?
Yeah, sir.
So that is the symmetry of the projectile motion. This fact is coming from the, so these are the coordinates of that highest point. They are the coordinates of the highest point. The y coordinate is h and the x coordinate is r by 2. So that point is also part of the trajectory. So it has to satisfy the equation of trajectory. So when we satisfy those coordinates in the equation of trajectory, that gives me a relationship between h and r, and that relation is in the step below, that h is equal to r by 4 tan theta. Now this relationship will hold true for all projectiles, regardless of how much the range is, how much the maximum height is. Any projectile having a maximum height h in meters and range in meters, you can find the theta from this relationship now, that h is equal to r by 4 tan theta. Now suppose, so hope this question is clear, people. Okay, now suppose this question had a second part. First was we wanted to find the angle of projection. Now the second thing is we wanted to find the height from the ground at an instant when its horizontal displacement is, let's say, 180 meters. Okay. So let's look at this second part now. So now that we have understood that in this type of question, it's always convenient to use equation of trajectory. So I'll go directly to the equation of trajectory method. Okay. So let's understand the second part of the question first. So in the first part, we've already found out that theta is 37 degrees. Okay. So we've calculated, and range was given to us as 240 meters. Maximum height was given to us as 45 meters. And the second part, what we have to do is basically we have to find y at the instant when, because y is the height from the ground when x is equal to 180 meters, because x is the horizontal displacement. So visually, if you look at it, let's understand the question first, then we'll come to the solution. So what we want to do is we want to find out that during this parabolic trajectory or during this projectile path, as it is going from here to here, it ascends to 45 meters and then descends, covering a total range of 240 meters. Now, as it is going through this entire path, at some instant of time, it must be somewhere here, where let's say distance is 180 meters. The x coordinate is 180 meters. So at that point of time, what is the y coordinate? That's what we have to find out. What is the height from the ground? So that is nothing but the y coordinate. So there must be some time when this is happening, some particular instant of time. It was projected at t equal to 0. So we have to find this y. So now the easiest way is we know this path, now the equation of trajectory. We already know it now because we calculated this thing. We calculated theta in the previous part. We just need to substitute. So theta is 37 degrees and r is 240 meters. So y numerically is what? 3 by 4x into 1 minus x upon 240. So now you can see this is the equation of trajectory in numerical form, where tan theta and r has been substituted. So now we have to just directly substitute this. So we have to find the height from the ground. That is nothing but y at when the horizontal displacement, that is x, is equal to 180 meters. So substitute this in this equation. Substitute. So y is 3 by 4 into 180 into 1 minus 180 by 240. You can see that this will become 3 by 4 into 180 into 1 minus, now 6 3s are 18, 6 4s are 24. So 3 by 4. So that is 3 into 180 by 4 into 4. Okay. So that is 3 into 180 divided by 16. So that we can now calculate. Okay. So if you divide 80 by 180 by 4, you will get 45. Okay. 4. So 3 into 45 will give us 135, right? Divided by 4. So that will give us 4. 3s are 12. 4. 3s are 12.75 meters. So this will be the height at that instant. So now we can see that, okay, this height will be how much now? This height is this one. So you can see how easy this question becomes because we are using equation of trajectory. And you can imagine how much lengthier it would have been if we had used the time-based equations instead of equation of trajectory. If we had used these equations that x is equal to u cos theta t, y equal to u sin theta t. So here we don't even know the value of this thing. No? We don't know the value of what we call it, the value of u to begin with. So we'd have to first calculate the value of u from the data given. Okay. Then substitute those here, then find the time t at which x is 180, and substitute that time in the second equation. So it would have been a multiple step process, whereas now this has become a single step process. So any question where you see that neither the data given has anything to do with time, nor the unknown quantity we are asked to find has anything to do with time. It's just the relationship between coordinates or positions or things like that. You can always try using the equation of trajectory as the first method, and you will see that that will give you a quick solution. Okay. So this is particularly for JEE advanced level questions. JEE mains is more like formula based questions. You should not have so much difficulty with those questions.
Yes, sir.
So can you just scroll up for the question for a second?
Second part of the question.
Yes.
Yes, this that find the height from the ground at the instant when the horizontal displacement is 180 meters.
Okay, sir. Thank you.
Okay. Okay, people. So hope this question is clear. It's done now. Now we'll discuss one more type of question. This is also a very common type of question in projectile motion which can be asked. So suppose we have this situation that we are firing a projectile at some given speed, let's say 50 meters per second, at some given angle, like let's say 53 degrees, like this, at time t equal to 0. Now in this question, we'll discuss a lot of aspects of projectile motion. So first of all, you will see that as it goes up, the angle of, actually my diagram is not that accurate, but the angle that the velocity vector makes, that will keep changing. Because remember, it has to become perfectly horizontal by the time you reach the maximum height. So it has to sort of curve like this. Then at the instant when it reaches the maximum height, it has to become like this. And then of course, it has to become like this. So at different times, you can see that not only the magnitude of velocity is different, but the angle it is making with the horizontal is also different. When it reaches here, so let's say some V1, when it reaches here, let's say it's some V2, reaches here, it's some V3, like this. And finally, when it impacts the ground, it is some Vi. So now this question is going to focus on this thing. Okay, so taking the value of G as 10 meters per second square. Okay, so given an object projected at t equal to 0 as shown, if V1 is at 45 degrees to the horizontal, okay, V2 is horizontal, and V3 is again at 45 degrees with respect to the horizontal. Then find the magnitudes of V1, V2, and V3, okay, and also find the time at which V is equal to V1, V2, or V3. Okay, what is the time at which the velocities values each of these? Okay, so that's the first thing. And second thing, find the final impact velocity, BI, okay, and the time at which impact with the ground occurs. This is the final impact. Okay, so this is a different type of question. Now you can see it is not to do with XY coordinates. Okay, it is to do with how the velocity is varying. So just, if you like, review the fundamental equations that we've discussed earlier about projectile motion, not the standard formulae, but the equations. Okay, and try to understand, try to correlate which set of equations we can use to get these answers over here. So a bit of time, I'll give you a hint. Just first try to figure it out yourself a little.
Sir, will you please confirm my answer so that I can like move ahead with the same concept?
Okay, Vedant, very good. No, the second part, beta, check the answer. V2 जो आपने दिया ना, उसका magnitude. You probably just made some uh, typing mistake. Okay, because Yashovardhan, impact means see it collides with the ground. No? Suppose you've thrown this ball or object from here, so kabhi na kabhi jaake it's going to hit the ground. So that impact means hitting or collision. Vedant, to answer your question, mod of velocity does not remain same, beta, because there is vertical acceleration. Only the horizontal component remains constant. You understood the point?
Yes, sir.
Jinendra, your answer is correct. Very good. The answer for V1's magnitude is correct. Okay. Now, before I get into the equations and things here, the first hint I will give you about how to solve this problem is just remember that in a projectile motion, as the body moves, the horizontal component of the motion, velocity never changes. That remains constant. It is the vertical component that is constantly changing. It is initially positive upwards, okay, decreases to zero, and then it becomes negative as it is coming down. So if you just remember that concept, then you'll realize very quickly what equations to use and how to use them over here. Okay. In fact, this is also not going to be a very lengthy question then. So it's projected at 50 meters per second at an angle of 53 degrees. Okay. So before we start with that, we can see what is the horizontal component of velocity. It is u cos theta, which you will see is 30 meters per second. And the vertical component of velocity is u sine theta, which is 40. So now as the projectile progresses, it goes in this parabolic path. Actually, the impact thing too, you can answer directly because you know the symmetry. So you know that the speed with which it impacts will be 50 only. There's no doubt about that. Okay. So that question is kind of like, it's a direct question. It's not. But also when it reaches the maximum height point, that is when the velocity becomes horizontal. We know this. So this velocity will become u cos theta, which is 30 meters per second. But this will be at time t by 2. Okay. That is the maximum height position. Whereas the impact speed, this also we know for a fact, it will be 50 meters per second. And this angle will again be 53 degrees. And this will be at time capital T. Now capital T was 2u sine theta by g. So that is going to be 8 seconds. We know that this time is going to be 8 seconds. This time is going to be 4 seconds. So this we already know. Okay. Now let's come to this part. So at this some point of time over here, if the velocity is v1 such that the angle it's making with the horizontal is 45 degrees. This is what is given to us. Okay. Now if you compare this situation with here, the horizontal component of velocity always remains constant. So this Vx will remain equal to 30 meters per second. Okay. So at time t, remember any time t, Vx remains u cos theta, which in this case is 30 meters per second. But it is Vy which is changing with time. It is u sine theta minus gt. So in this case, it is 40 minus 10t. This is the instantaneous value of this. Okay. Now, if we want that this angle is 45 at this time, let's say t1. Okay. If this angle is 45, then what should be the value of Vy? It should be equal to Vx. No? It's vector algebra. If this velocity v1 is such that it's making an angle of 45, then its horizontal component and its vertical component should be equal.
Yes, sir.
So at t equal to t1, v is equal to v1, which is at 45 degrees with respect to x-axis. Okay. So therefore, vy by vx, which is your tan 45, should be equal to 1. So vy should be equal to vx, should be equal to 30 meters per second. So that means 40 minus 10 t1 should be equal to 30, which means that the time is 1 second. So at 1 second, the velocity has changed from the initial velocity, which was like that, to this velocity v1, which has become now 30 I cap plus 30 j cap in meters per second. So its magnitude has, as you can see, become 30 root meters per second. Okay, because the initial velocity was 30 I cap plus 40 j cap at t equal to 0. 0 to 1 second, this is what has happened. The velocity is changed from this to this. Okay. Now further, you can see that this velocity at t equal to t2, the velocity is, let's say, v2, which is horizontal. So if it is horizontal, that means v2 should just be equal to 30 I cap. Okay. The y component should become 0. So the time will be equal to 4 seconds, you can see, because vy is 40 minus 10t. So that's that part. Now similarly, you find for this one, at some point of time here, t3, let's say, the velocity is v3. Now v3 is also at 45 degrees with respect to horizontal. So just like I've done for v2, for v1, use the similar method for v2. For v3.
Sir, this can be done by symmetry also, right?
Exactly. Now you can see that t1 and t3 are symmetrical times. So it's even more convenient. Okay. So t1 plus t2 should be equal to how much? The capital T, the total time of flight.
Yes,
Is that
sir.
symmetry? Directly you can see. And the magnitude of v1 should be equal to the magnitude of v3.
Yes, sir.
Only the y component is reversed. That one is 30 I cap plus 30 j cap. This one should become 30 I cap minus 30 j cap.
Sir, was there any second part of this question or this one only?
Sorry, wait, what was that again?
Is there any second part of this question or just like this time and velocity?
Just we have to find these times and magnitude of velocity. And impact velocity. Impact velocity to nikal liya humne already. We know it will be 50 meters per second. The second part is actually done already. Now we just need to calculate for that v3. So for that v3, I'm just making the diagram again separately. So v3 is a velocity like this, where with the horizontal the angle is 45, means basically this angle is 45, or even with the vertical it will become 45. So now remember, horizontal component of velocity is remaining constant, that's not changing throughout. So this must be 30. Okay, but if this angle is 45, that means the y component of velocity has actually now become minus 30 meters per second. So you can understand it that way. Okay, so this is at t equal to t3. So Vy should become minus 30 meters per second. So Vy is basically what it is, u sine theta minus gt, or it is 40 minus 10t. So that should be equal to minus 30. So you can see that the time should be equal to how much? 7 seconds. But also, like you very correctly said, that so much calculation is not required. We can just notice the symmetry between T1 and T3. If you notice the symmetry between T1 and T3, then T3 becomes more direct. We just needed to put effort to find T1. So if this was the time when the velocity was V1 and this angle was 45, and later on, again the angle became 45 but with a negative direction. Okay, so this was our V3, but because this angle was 45, you can see that there is this symmetry now between these two times. Okay. So from symmetry, you will see that mod of V3 is equal to mod of V1, which is 30 root 2 meters per second, and T1 plus T3 should be total time of flight. So T3 should be capital T minus T1. So that also shows why it is 7 seconds. Okay. And of course, V3 in terms of a vector is 30 I cap minus 30 j cap. Okay. So the magnitude of V3 is 30. So that's why I told you always that for advanced type of questions, the symmetry is something which is very useful to keep in mind. The symmetry of the ascending part of the motion and the descending part of the motion. It makes a lot of things quite simple. Okay, so hope this question is clear. And of course, the second part, the impact speed, we know that that should be equal to the projection speed. So it should be at 50 meters per second, or the velocity of impact will become 30 I cap minus 40 j cap. Okay, because at t equal to capital T, what happens is that Vy becomes minus of u sine theta, which in this case is 8 seconds.
So Vi would be minus 50, right?
But that's magnitude, na? So magnitude always comes without sign. Understood, na?
I thought you asked Vi.
Nee, a component of velocity can be negative, like the y component is minus 40, you can see. But the magnitude of a vector quantity is never expressed as a negative quantity, na? Or positive for that matter. It simply does not have algebraic sign. Understood, na? it's a speed, no? It's impact speed. It's not a vector quantity, so we will not give it any algebraic sign. Okay, so now we come to the next section of projectile motion, okay, which is projectile motion from a heighted point. We're doing the projection from a height, not from the ground level. So the first case we will look at in this will be when we are doing a horizontal projection from a height. That is, like, let's say the person who's projecting the object is standing on a tower or a building or whatever, but he or she is at a certain height above the ground, and now they are projecting from that height above the ground with a horizontal velocity. They are giving the object that they are throwing a velocity which is horizontal. So this object is thrown from here. It is projected or it is thrown with a horizontal velocity. At t equal to 0. Some object is thrown here. So what will happen is it will have this kind of a path as it falls. Because of gravity acting on it, it will curve and eventually it will hit the ground. So this is the impact, so, which is happening at time t, and this time, so let's say this height from which we are throwing it is capital H, okay, and this distance at which it lands is r, and at some intermediate time in between, let's say it's over here, so it has a velocity v and it has coordinates x and y, whatever. So in such a case, what we do is we take our reference frame such that we take again the origin at the point of projection. Most convenient way of doing it. We can also take the origin at the ground level, but more convenient will be this. But the y-axis is downwards because so the reference frame says that origin is at point of projection. X-axis is horizontal and y-axis I'm taking vertically downwards now. You can take it upwards also, but most convenient will be to take it vertically downwards. So that, okay. So now we can see that at t equal to 0, the projection velocity is ui cap. So when I divide this into components, ux is 0. Ux is u, my mistake. And uy is 0. Whereas the acceleration is gj cap because the y-axis is pointing downwards. So the acceleration's x component is 0, but the acceleration's y component I'll this time write with a plus sign because I've not taken the upward direction as vertical as the y-axis. I've taken the downward direction. So from this now I can write that at some time t.
Sir,
Yes,
sir, why AX is 0?
because only gravity is acting on it. Okay? As the particle moves, the net force acting on it is always mg, which is vertically downward. So there's no force giving it a x component of acceleration. You understood, no?
Yeah, sir.
Okay. So at some time t, the x component of velocity will be u and the x component of displacement will be ut. Whereas the y component of velocity will become gt and the y component of displacement will become half gt square. So the velocity at such a time would have changed from just ui cap to ui cap plus gt j cap. But remember that plus gt does not mean vertically upwards here. It means downwards because the y-axis is downwards. So this is the velocity as a function of time, and these are the coordinates. as a function of time. So just make a note of this first, and from this try to develop the formula for range capital R. Okay, so next thing we'll do from this, using these we'll find capital R, we'll find the time at which it impacts, and we'll find the impact velocity. So see if you can figure out how to calculate these three quantities from the equations that we've developed, the equations which I've tick marked, the coordinates as a function of time and the velocity as a function of time. It's very easy. Okay, it's quite simple really.
Sir,
Yes.
so in this case, we can even take it like half the motion of projectile motion from the ground. Like it is
Yes, you
the
can
half
think of
part.
it like that. Suppose we had projected from somewhere behind like this, okay, and it went up and came down. Then at the highest point, whatever its situation would be, that is the situation actually where it is now at t equal to c. That's correct. So we can take a comparison with a regular projectile motion and understand it that way also. Okay, so from this now you can see that as a formula, if we develop this, we'll see that at time capital T, when it impacts the ground below, okay, what happens is that the y coordinate should become capital H. Okay, so from this second equation, so from equation 2, we have that H should become half GT square. So the time it takes to reach the ground is given by this formula, square root of 2H by G. And it is at that instant of time, okay, the x coordinate is nothing but r. So from equation 1, you can see that r will become u into capital T. So in this case, the value of capital T that we just calculated is square root of 2h by g. So this will give us this. Okay. And from equation 3, we will see that the impact speed will become u I cap plus g into capital T j cap. So you will see that the impact velocity is u I cap plus root 2 gh j cap when you substitute the value of time. So we are substituting capital T here. Of course, we are substituting capital T here also to get these. So this gives us the three important things. Okay, the time, the distance at which it lands on the ground, and the impact velocity. Okay, people. So hope this is clear. Let's look at a quick example problem. Let's say what we're doing is we're throwing an object from a height of let us say 320 meters, and we are projecting it with a horizontal velocity of 60 meters per second horizontally at t equal to 0. Take the value of g as 10. So at some time it will land on the ground with some impact velocity. So now we have to calculate various things. So standard things first, find this time, the range at which it lands, and the impact velocity is magnitude. Also we have to calculate the angle of impact, that is the angle made by the impact velocity with respect to the ground when it hits, at what angle it hits. This is the impact velocity of ground. Okay. And we also want to find out the velocity at In fact, we'll find out velocity and displacement, two things, at t equal to 2 seconds. So just try this out. In fact, instead of 2 seconds, let's make it 6 seconds. Easier. Yeah. Okay, so more or less you have to use the standard formula that we just discussed about. This is not a very difficult question in any sense. Okay, just try this out and send me the answers. Okay, so number of people have sent me the answers. Vedant, your answer is also correct. So I'm not sure if you're online right now. Yeah,
Yes, sir, I'm there.
yeah, then okay. Yeah, so that's correct. Jinendra, your answers are also correct. Very good. Okay, so for the first part, we can just use directly the formula only. You can see T is equal to square root of 2h by g. So that will give us the time as 8 seconds. Then basically it's u into t. So it becomes, so in this case, it becomes 60 into 8, 480 meters. So it lands at a horizontal displacement or horizontal range of 480 meters. And the impact velocity we can see is ui cap plus root 2 gh j cap. So that will be here 60 I cap plus 80 j cap. So the magnitude of the impact velocity or the impact speed will become 100 meters per second. So you had thrown it at 60 meters per second, but because of gravity, it will develop a vertical component of velocity. So while the horizontal component remains constant at 60 meters per second, but at the time of impact, along with that horizontal component of 60, it has also got this velocity of 80. So that brings us to the second part of the question. So for this part, you can understand that the impact velocity that we've written over here is 60 I cap plus 80 j cap. So if we just draw a vector diagram, it just makes things much more clear. So the horizontal component is 60. The vertical component at the time of impact is 80 downwards. So that means the velocity vector itself is this, right? This is the impact velocity. And this is the angle we are talking about, this angle. So tan theta will be that vertical component divided by horizontal component, 4 by 3. So you can see that it will impact at 53 degrees with respect to the horizontal. So that is the answer of the second part of it. Whereas the third part, we have to now use those kind of equations that if we project it from here at t equal to 0, this then as it moves at some time t, the velocity vector is ui cap plus gt j cap. The x coordinate is ut, the y coordinate is half gt square. So we can see from this that at t equal to, what is it now, 6 seconds, you can see that the velocity vector would be 60 I cap plus 60 j cap. And the displacement will be 360 I cap plus half gt square will become half into 10 into 36, right? So 180. This will be the displacement in meters. This will be the velocity in meters per second. Basically, this will come from this, that x will be 60 into 6, 360. Y will be from this you're getting the displacement. Okay, so hope this question is clear. Okay. So going back to the original diagram, you'll see that this distance comes out to be 480 meters at which it lands. Okay. Impact velocity already I have shown you in the diagram, and this time works out to be 8 seconds. Whereas you realize that at t equal to 6 seconds is probably somewhere here. So, so y is 180 means basically this thing here is 180. Okay. And x is, how much is it now? 360. So this distance is 360 meters. Yeah, just a minute. Okay. Now, for example, if you also want to find out that what is the height from the ground at this point of time, so you'll see that this height from the ground, that height h will be how much? This is 320. So 320 minus 180. So that will be how much? 140. Right. So at this time, 6 seconds, it is at 140 meters height from the ground. Okay. Additionally, there is that thing. The y coordinate is 180, means that the height from the ground is capital H minus y. I hope this is correct. This is clear now.
Sir,
Yes.
sir, I noticed the thing will you please confirm, is it coincidence or like obvious, sir? I took a ratio of the distances and even the time periods. So the ratio is coming in square, like distance is 3/4, so it's time is coming 9/16. So it's like we can use this relation in each and every sum, or like it is coincident over here.
It's coincident over here, beta, because actually the relationship is like this, that whatever is the ratio of the time, that will be the ratio of the horizontal displacement, because the horizontal displacement is linear with respect to time. No?
Yes,
Whereas
sir.
the vertical displacement, the ratio will be in square of time, because vertical displacement is what, half gt square. No?
Yes, sir. Yes, sir. So it came square only. So we
But
can use it.
that's the vertical displacement. You know? But the
Huh?
overall displacement, that you will have to see. Okay. So basically y divided by h, capital H, this will be equal to t divided by capital T whole square. Why? Because y is equal to half gt square, right? And h was equal to half g capital T square. Whereas the x component of displacement with respect to r will be the direct ratio of t by r, because x is ut and this horizontal range is u into capital T. Understood? No?
Yes, sir. So means we can keep this in mind for fast calculation and all.
You can use this also for fast calculation. Okay. Okay. Now we come to the final part of this projectile motion from heightened point. So that's the second case. Okay. Oblique projection. That means projection at some angle from a height. So within this also you can see that can be two types of oblique projection. One where it first ascends and then descends, because the angle is upwards with respect to the horizontal. Or there can also be a case where it directly comes down because we are throwing it at an angle which is giving it a downward component of initial velocity. So both such cases are possible. Okay. I'll just go back to the previous line once you can finish writing that. Yes, and then come back. This one, huh? The one with the diagram you said. Main diagram. Okay. Yeah. Okay. Yes. Yes. This is clear now. Okay. Now we will understand these two cases of oblique projection directly with examples. No problem. So in this case, let's say we are projecting like this. Say we are projecting at an angle of 30 degrees with the initial speed of, let's say, 40 meters per second. Okay. And this height here is, let us say, 60 meters. Okay. So this will go up and then come down. And at some point of time, it will hit the ground. Some kind of range. And another case that we could have is this. When we have projects, again, just taking the same value for simplicity, but the method we will develop is general. So this kind of an object will have a much simpler path. It will come only with descending straight away. So what we'll do is, when we choose our reference frame, we'll have a slightly different approach for the left side one and the right side one, because this one is first ascending. So we'll take the y-axis upwards, and this one is straight away descending. So it will be more convenient to take the y-axis downwards. So there is no hard and fast rule written in stone that we have to do it this way, but this is the most convenient way of taking the reference frame. So for this one, you can see the left hand side one, the initial velocity is u cos theta I cap plus u sin theta j cap. In this particular case, that will become 20 root 3 I cap plus 20 j cap in meters per second. And the acceleration will be minus gj cap. So the acceleration vector will be minus 10 j cap. The acceleration is downwards. Whereas in this case, because I've taken y-axis downwards, again the initial velocity is by the same formula, u cos theta I cap plus u sin theta j cap. But this time this is a downward component, whereas here this was an upward component, because the y-axis is different. Okay. So the initial velocity here is 20 root 3 I cap plus 20 j cap again. The acceleration therefore will be written with a plus sign now. It will be gj cap, or the acceleration will be 10 j cap, even though it is downwards basically. So next, so just make a note of this much first. Next, what we'll do is, again, we'll divide this into components, the individual components of motion. And from that, we will develop the formula for time, range, r, and impact speed. Okay. So let's proceed with this now. So in this case, you can see that ux is u cos theta or 20 root 3 and ax is 0. So at any time, okay, whereas the y component is u sine theta, so 20, and the y component of acceleration is minus g or minus 10. So from this, we will see that the y component of velocity at any time is u sine theta minus gt, or in this case 20 minus 10t. And the y component of displacement is u sine theta minus half gt square. So 20 minus 5t square. So these are going to be the most important equations, this and this. So I'm going to solve this part first fully, then I come to that part. So now when it lands on the ground at t equal to capital T on impact, firstly, what is happening? The y coordinate is becoming minus of h. That is minus of, what was it? 320 meters. So it's 320 meters downwards now. And the x coordinate is equal to the range. So from equation 2, we will get that minus 320 is equal to 20 minus 5t square. So 20t minus 5t square.
Sir, it was 60 meter.
Sorry?
60 meter it was, sir, height.
Acha, 60 meters. Okay. So that is 60. Okay. Yeah. So minus 60 meters. And this equation should be 20t minus 5t square. Okay. So from this, we'll get minus 60 is equal to 20 capital T minus 5t square. So just divide the equation by 5, okay, and transfer the terms a little bit. So we will get this. Okay. So this will give us see the roots will get
It will be 12, right? T square minus 40 minus 12.
oh sorry, my mistake. We're dividing by 5 and not by 4. Okay. So yes, correct. It should be 12. So I think this should be easier to factorize them. Sum of the roots is 12 and products of the roots is minus 4. So
6 and minus
6 and minus,
Sir, minus 6 and 2.
no, the, yeah, I
the
mean,
roots will be T minus 6 and T plus.
okay. So the value of t is either 6 seconds, which is acceptable, or minus 2 seconds, which is not acceptable because time should not be negative. So now we can see that at this particular time, the value of x is equal to the range. Okay. So from equation 1, you can see that r will be equal to 20 root 3 into capital T. Substitute this here. So the range is 120 root 3, or you can approximate that as 120 into 1.73 whatever that final value comes out to be in meters. Okay. And now from this, you can also see from this equation and this equation, the velocity as a function of time is how much it is 20 root 3 I cap plus 20 minus 10 t j cap. So from equation 3, velocity is the impact velocity. So from equation 3, the impact velocity will become 20 root 3 I cap plus 20 minus 10 into 6 j cap. So you can see the impact velocity will have a horizontal component of 20 root 3, but a vertical component of minus 40. It's kind of thing. So I've got the time, right? I've got the range, I mean the horizontal displacement at impact point, that range, and I've got the impact speed. So like more than, don't think of this like direct formula or something, just understand how we take the reference frame, and from that reference frame we write these equations. These are the component equations. Okay, these are the most important things. This is the x component of motion, and this is the y component of motion, or the vertical component of motion. And now using these fundamental equations only, we can find out any of these quantities which are required. Okay. So I want you to go through this very carefully, and the other part of this which I had written on the side, where the projection was happening such that, you know, the vertical component was downwards rather than upwards. I want you to try that yourself. Okay. I will just give you the answers for this part. Try yourself when you're revising, and check that you should get the answers like this. You will get the time as 2 seconds in this case. Okay. And you will get the impact velocity as 20 root 3, but plus 40 j cap. But the plus actually still means downwards only. And here also the minus 40 meant downwards. Okay. And the horizontal range you will get will be 40 root 3 meters. So when you're revising today's lecture, just go through the working of the first case and then work out the second one yourself. Okay, so with this, we are done with projectile motion, and you can go ahead and solve all the questions from HC Verma and projectile motion. Okay. I will send you a list of the exact questions plus a revision worksheet also. Next lecture that we have, we will keep fully for problem discussion first of all. Okay, so we'll discuss the problems of projectile motion as well as problems pending from one-dimensional motion from the worksheet earlier. Okay. And then only we'll move on to the last part of kinematics, which will be the relative motion part. Okay. So that's it for today's session, people. Wish you all the best and thank you for attending. Have a nice day.
Bye, sir.
Yes, sir. Thank you, sir.
Thank you, sir.
Thank you, sir. Bye, sir.
Bye.